Thank you all. It is my absolute pleasure to talk to you tonight about before Boaty McBoatface. So on the right-hand side there, you'll see AutoSub for autonomous submarine, LR for long range, Boaty McBoatface. That is the current incarnation of the autonomous robotic submarines being built at the National Oceanography Centre, Southampton, just through Dockgate 4. But I'm going to talk about AutoSub 1, 2, 3 and 6000. They're the ones that were built by a group of engineers at the Oceanography Centre from about 1990 to I retired in 2012. So it's before Boaty is what I'm going to talk about. Now, the AutoSub project itself was in the group that I led. Peter Collar, Nick Millard, and Steve McPhail were the team leaders for AutoSub over 30 years. And it is them and their colleagues whose work really I'm trying to celebrate with you tonight. Now, it's not the done thing to show photographs these days, so I've made this fuzzy. But in there, you'd see if there were characters in the book, there would be the Director General of Research Councils. There would be the Chairman of the Natural Environment Research Council. There'd be the insurer who accepted an insurance premium for insuring this vehicle. There'd be the scientists, there'd be the engineers, there'd be the technicians, there'd be the lawyers. Could we deploy this robot submarine legally in the ocean? All of those people are represented there, and it is their collective efforts that I'm going to show this evening. So what makes up a robot submarine? On the left-hand side are little instrument cases with connecting cables that we'll get to meet some of them along the way. And in yellow there is a fairing. That's just part of the structure surrounding the space frame to make it a streamlined shape. And at the back, behind that large metal dome, is the propulsion motor. Think of a washing machine motor. Think of something less than 1 horsepower is the electric motor for this submarine. It doesn't go fast. It'll go 4 miles an hour maximum. What's not shown there, batteries not included. And we'll come on to why in a moment. And there, boringly, on the right-hand side, are the names, the titles of all the subsystems that are inside those electronic housings. And those were coupled with a network called Lontalk, twisted pair, akin to a very slow USB bus. That's how I can characterize it for today. So the communications happened on those cables and the power went to the different modules exactly like you would have an USB device hooked up to your computer. And that is really what comprises those modules, a robotic underwater submarine. So with all of those and 20, 30 years of work to pick from, here's the outline of my talk tonight. I'm going to really concentrate on 4 areas. So how did they advance knowledge and practice for deep ocean pressure vessels? This is what was needed to house those batteries, what was not shown in the previous photograph. Why, for years, did they use 5,000 of these? There we are, the humble D-cell. They did get a good quantity discount each time. Made up into battery packs. Why did they use something as humble as that? Then, with what success or not, judging by that photograph C, there's an example of not, did they handle collision avoidance? This is an autonomous robotic submarine. There is no communication whatsoever with it once it's underway. It's got to look after itself. Sometimes it misses. And then D, how did they answer my lab director's question? What's the chance of getting it back? So those are the 4 areas for my top talk tonight. Now oh, good Lord, I've missed out a P. When the pressure gets too much, I drop a P. Oceanographers are all too familiar with these problems of designing and using pressure housings for equipment. So these are some that were retrieved that went wrong. So stainless steel there on the left, glass spheres, a speciality there of John Gould's. The glass spheres are inside those yellow housings, and when one of those implodes, so it's not explosion, it's implosion because of the pressure, the glass ends up as a funny sort of white powder, complete change of substance. Aluminium end domes that cap off the tubes, they can crack and fail. And then crushed filament wound carbon fiber tube showing delamination. The layers of the carbon fiber tube have come apart. That's what we don't want to happen to our autonomous vehicle. That's going to cost about £1 million. So pressure vessels aren't new, they're used in submarines, so what's the big problem? Well, here we have on the right a submarine, a US submarine, over about 2,500 tons. She has a depth rating of 120 meters. 120 meters. We want to go to 6,000 meters. So she's in steel tubular sections with ring stiffening. Now here's a clean can of that did hold tomatoes. This is a ring stiffened can along there. So that adds rigidity. It's harder than it would be for me to try and crush this can if it wasn't for these ring stiffeners. So that's what you'd find inside a submarine. Submarine hulls are ring stiffened steel structures. The pressure vessel generally sets the maximum working depth. It's going to be the largest pressure system inside the vehicle. It's going to be the most expensive part of the pressure housings in the vehicle. And we needed to provide dry space for these batteries, 5,000 of them. We need dry space for the electronics. We needed to contribute to the buoyancy of the vehicle. There's no problem with that submarine. Look how high it's floating in the water, even though it's made of steel. It's got an enormous buoyancy reserve, but it's far more challenging for a 6,000 meter vehicle to have enough buoyancy that you can float all the heavy parts in the vehicle. And it's got to be trustworthy. It really does, with a known margin of safety, because failure would inevitably mean loss. So what are candidate materials then? And we come on to some peculiar units here. You've all come across specific gravity. So specific means you're taking account of the weight. Now here's a unit, specific strength. It's the cube root of Young's modulus, and Young's modulus is the ratio of stress over strain, how a material takes to external pressure, divided by the density. So our reference is aluminium, a particular alloy. You've got to be very careful with alloys. So this is a high-strength aluminium alloy, which is our reference strength, specific strength of 1. Stainless steel is less than half the specific strength of aluminium. When you take the high density, 7,960 kilograms per cubic meter, high density of steel, specific strength is poor. We're never going to make a steel Boaty McBoatface. Titanium, terrific alloy. Its Young's modulus is less than steel, but the density is much lower, so it's much better than stainless steel. So that's a candidate, but it still doesn't beat aluminium, but it's more corrosion resistant than aluminium. So that's a mark in titanium's favor. And then there's carbon fiber. This is so seductive. 190 for the Young's modulus. The density there is low, and our specific strength, 2.43. Along the axis of the fiber. Along the axis of the fiber. At 0, at 90 degrees across the fiber, it's poor. And so the engineering material science challenge is, how do you maximize the property of the complete carbon fiber pressure vessel given those two figures? But is it trustworthy? It's anisotropic. It has material properties that differ depending on its direction. But it's so promising. Now I'm also going to pass around a photograph. I can't include that in a slide. But the buoyancy contribution I've mentioned, look at that blue arrow on the middle one. That blue arrow shows the collapse pressure for a submarine. That's where we are for a submarine. It doesn't really tell us anything at all about the area that we'd like to be up here. 6,000, 60 megapascals, 6,000 meters depth. So we're going to work up here. That's where a submarine works. So it's very little for us to take home. And aluminium, if we're trying to work up here, there's hardly any contribution to buoyancy. Same with titanium, unless we ring stiffen it. So it would be good, titanium up here. But look, carbon fiber gives us all this buoyancy. It's such an attractive material. And so the lab at Southampton took part in a major European research program with many institutes, especially in France and Greece, and the Defence Research Establishment in the UK, to try and push forward the technology of carbon fiber pressure vessels for use in deep ocean vehicles. And they did successfully manufacture and test a half-scale prototype to 6,000 meters. But look at their conclusion. Does this give you confidence? Difficult to give authoritative recommendations, and with no guaranteed operational depth and an adequate margin of safety. Those are woolly words, really. You'd probably be put off, but we weren't. We went ahead in 1999, 3 years after that project, with UK manufactured carbon fiber reinforced plastics. The picture that's going round is from the Defence Research Agency, where they wind the cylinder, and you can see the process in this photograph, where individual fibers wound onto a mandrel, which forms then the tube, and those fibers pass through a bath of epoxy adhesive, araldite. And those fibers pick up the adhesive, they travel onto the cylinder, and it's wound at a cross angle of 55 degrees to try and maximize that property. They were too expensive. They lost out in the competitive tender to the only one other supplier in the UK that has that manufacturing capability, Urenco, an acronym for the Uranium Enrichment Company, part of British National Nuclear Fuels, based at Capenhurst in Cheshire, where they manufacture carbon fiber pressure tubes for use in ultracentrifuges for the enrichment of uranium. They were cheaper than the defense company. And they wound them for us. The design was for 4,500 meters with a safety factor of 1.8. We want to be careful. So it should have got crushed at 4,500 meters. But the test sample didn't survive to 4,500. It was crushed at 3,200. We go back to those careful words of the European report, we can't guarantee. And so what we had to do, was to derate the Autosub vehicle to set its working depth at 1,600 meters, which would give us a safety factor of 2 on the crush depth. And indeed, there were no problems at all with the carbon fiber pressure vessel. I don't normally put this many words on a slide, and they're not meant for you to read at all, but they're meant for you to take away a message. And the message is of the central importance of technical staff to this. It's not just all highfalutin science or engineering or PhD level. It is the careful expertise and application of that expertise by technical staff to procedures here, such as gluing a titanium flange onto the end of the tube. So another trouble with carbon fiber tube is, well, how do you put an end cap on it? How do you close off the end? You can't machine it in the same way as you can titanium or steel. So you have to glue a titanium ring If you imagine that goes round the cylinder, you have to glue this titanium ring to it, and then here we have a titanium end dome, and this stress analysis shows that this is really a critical area between the bond, the transition ring, and then the end dome. And that gluing there has to be absolutely perfect. They tried epoxy adhesives, no good. They went through a list. Polyurethane adhesive is what has worked, and this was part of their procedure, the written procedure for doing that, with monitoring temperature and humidity and time and checking for inclusions. And there were no failures on their part. So I do stress the contribution of technical staff. So where are we now? We're at the stage where we have a vehicle. We have these carbon fiber pressure vessels. We have syntactic foam buoyancy around each one of those. So it's like having 7 cake segments, the yellow syntactic foam. And what do I mean by syntactic foam? It's araldites, it's epoxy adhesive. And inside that are tiny, very small glass microspheres. So they are air-filled tiny spheres of glass, which means that a block of this syntactic foam would have a density about half that of water, and it can withstand 6,000 meters. And that's what gives us the buoyancy to float all of the metal parts of an autonomous underwater vehicle. So now we have the pressure vessels, we have the carbon fiber pressure vessels. Now we're going to go on to those batteries, those dreaded batteries. Right. So we're designing an autonomous, robotic, entirely self-contained submarine. And in the back of our head is always our lab director's question, what's the chance of getting it back? Now let's look at some performance figures here, where we're going to have a look, the technical of you can look at the specific energy, how many watt hours there are in a kilogram weight. And at that time, silver zinc, as used in torpedoes, was the number one, the one to beat. Lithium ion back then was about 130. It's higher than that now, maybe 200 or so. Manganese alkaline didn't do too badly compared to lithium ion back then. But look at the cost, £5,000. Can you refuse this £5,000? Lead acid aren't too bad, but you don't get much range compared to the alkaline batteries. So it was in a way a no-brainer that we could afford £5,000 to fill the tank, because I just would not have believed that we would have had enough missions until we lost the vehicle to have more than 10,000 kilometers. So this was a cost-effective power source, the humble D-cell, 5,000 of them. But still we try to maximize performance. So there are 75 D-cells in series, and then 68 of them in parallel, forming a battery pack like this. And they would go inside the lower 4 of these carbon fiber pressure vessels, and you can see the titanium flanges on the end of these tubes. So these 4 are the carbon fiber pressure vessels, and the top 3, those 2 and the center one, are there to give buoyancy. And so these bottom 4 are filled up with these battery packs, and we insulate these battery packs, thermally insulate them, so that we use the waste heat generated by I squared R, the current squared times the internal resistance of the batteries, gives us some heat, which keeps the batteries warm for when you're operating in polar waters. We all know that generally in cold weather, batteries don't do as well as in warm. So we make use of the waste heat. So let's go on to an example of what on earth we were using this autonomous underwater vehicle for. So this is the torch battery era, Autosub 2. It's in the Antarctic. So this is the Antarctic Peninsula. South America is up here. South Africa is up there. And the 3 scientists, this is back in 2000, 2001, and it was one of my biggest delight, really, to work with young scientists who had creative ideas, creative hypotheses to test. And they wanted to know what was the difference in the population of these krill, shrimp, at the base of the food chain in the Antarctic for marine mammals. So krill in the Atlantic, South Atlantic, into the Weddell Sea, Antarctica. What was their population density in open water and then underneath the sea ice in this area? So there we have our AutoSub vehicle. It's on the gantry. It's about to be launched. And it's got an echo sounder in it. So here's this cartoon. So I'm down at about 120 meters down, in this case, for this mission. Here we have the AutoSub. We have an echo sounder with its beam looking up. And it's giving us echoes back. And the echo strength is the colored blobs, from blue for weak echoes to red for very strong. And these blobs here are swarms of krill. And from the strength of the echo, then the scientists could figure out how many krill there were per cubic meter in this area. And then the beam also reflects back from the underside of the sea ice. And so by doing this, you can see they can measure the sea ice thickness as well. So you're satisfying the biologists with the krill measurements, and the glaciologists and sea ice physicists with some measurements of sea ice thickness. And we repeated this several times in open water in red and under the ice in yellow, and they come up with the answer. Distance from the ice edge, 0 is the ice edge. This is open water out here. Relatively low values of biomass, grams per square meter. But here we have, in this narrow band, 10 to 12 kilometers into the ice, then a much higher density of krill. And this was the answer that they sought. And they had error bars from it, which was brilliant. And so it was no surprise, really, that those three scientists, those young scientists at the early stages of their career at that time, each of them became a professor at a major UK university. So really, in part founded by the attitude, their approach to science, but their achievements as well. But now we only have an autonomous vehicle for 1,600 meters. Our goal is to 6,000 meters to be able to get to the bottom of most of the world's oceans. So how are we going to do that? Well, we'd shown enough science success by 2005 that we could make a credible case for funding for a deeper diving vehicle. It had been very successful indeed. So how had carbon fiber technology moved on to 2005? Well, there was this wonderfully named the Worldwide Failure Exercise, that for carbon fiber and laminate substances, they looked at 19 theories of composite material failure. Now, as a practical engineer, that tells me something. If you've got 19 theories of why they fail. So, no, we gave it up. We tried. We'd been there. We could not achieve our diving depth with carbon fiber. So the answer for AutoSub 6000 was to use small, mostly titanium pressure vessels, as you saw in my first photograph. And let's use batteries that don't need to be in a pressure vessel. Okay, because there was a choice available at that time. And we'll use our old friend syntactic foam for buoyancy. So what batteries can we expose to the full ocean pressure? And I've just, for a little bit of fun, hopefully you won't see that from the back, but that's such a tiny piece of yellow post-it note. That's 1 square centimeter. So the pressure of the ocean water on each square centimeter at 6,000 meters is 612 kilograms on each of the square centimeter. And what battery can take that pressure? The lithium polymer battery in your mobile phone. It's entirely solid state. There is no air gap or no void inside it. So it's somewhat similar to exposing a piece of plastic to that pressure. So those batteries, they will survive. And there was a track record. Previously, for some uses, you could take a lead-acid car battery and the old-fashioned type with pots that you could open up here. And instead of topping it up with water, you top it up with oil. so that the entire battery casing there is filled with liquid, with the dilute sulfuric acid for the electrolyte, and then with oil in the rest of the space. And that would work underwater, but it's far too heavy, not enough energy. So, especially these batteries from Cockham, the lithium polymer pouch cell, completely solid state. Now we're running these completely beyond a manufacturer's specification. No sensible manufacturer would guarantee that these would work at full ocean depth. Just put them in a container of oil so that they don't short out, and then expose them to deep ocean pressure, 60 megapascals, the equivalent of 6,000 meters. And I also want to say how students and at master's and doctoral level also contributed to this project. And Kieran Rutherford, an engineering doctoral student, looked into the details of the effect of pressure on those lithium polymer cells, as in your phone. And there was an effect. So this is the cell voltage, so the voltage of the battery against state of charge. So here it's 100% charge, and I'm just going to take the pair of graphs here that are red and green. Green being at ambient pressure, 0.1 megapascals, and then red at 60 megapascals. And there is a small difference. It's small, and it maintains there, and what that means is that the cells, when they're under pressure, have a slightly higher internal resistance. Their voltage drops a bit lower when you're taking current from them at 60 megapascals than it does at the surface. And when you do the calculations at 18 degrees C, 60 megapascals, 54 milliohms internal resistance, 49 they're ambient. So a small difference. But look, if you took the temperature down, at atmospheric pressure down to 4 degrees C, the internal resistance would more than double. So the effect of the pressure is tiny compared to the change in temperature. So we knew that we had a suitable battery technology, so we had to put them inside a case made of our favorite material, titanium. It's filled with oil, and it has a polyurethane diaphragm there. So why does it have a diaphragm? That's to accommodate the change in volume of the cells with state of charge. Now, you wouldn't notice inside your mobile phone, but your battery size, the thickness of the battery, changes with state of charge. It's 2% thinner when it's 10% state of charge compared to 100%. So, not much, but if you put that into a solid substance, it would crack it immediately. So that's why there's a polyurethane lid on it, to allow for expansion with state of charge. Now let's go back to some achievements from this AutoSub 6000. And indeed, Professor Weaver could speak far more eloquently of this slide than I could. This is to show that there were unique scientific data being returned by these vehicles. For the first time, autonomous vehicles could get down to those depths. So we're now, there we are, AutoSub 6000, looks much the same. We're in the Bay of Biscay. This is up on the canyon area to the north side of the Bay of Biscay, UK is up here. And look at these wonderful features that a shipboard sonar will tell you about. The colors indicate depth, red being shallow, the deepest blues being the deepest part of the ocean. And look at this wonderful feature of a submarine canyon and almost like a riverbed, a sediment riverbed going out here into the ocean in the Bay of Biscay. So that's what a shipboard instrument would tell you, which is already a wonderful image. But now take the AutoSub vehicle down to about 4,600, 4,700 meters. And now you have the richness which the scientists here, Vila Havini and colleagues, Russell Gwyn, have delineated, that's showing them flows on the seabed, scours on the seabed, crests of sediment waves, and so on. And this really was unprecedented detail. That's the scientist's word. And that's how the engineers get their satisfaction, from delivering that important new science from the data. So let's move on to the area of collision avoidance. There are really 3 challenges in collision avoidance for an entirely autonomous vehicle. Can't call home to ask guidance when it's underway, only on its surface. So you have to detect a potential collision hazard, and you do that with sonars. And you may have a sonar looking up, a sonar looking ahead, and the sonar looking down. Because in open water, your most likely hazard is the seabed. That's most likely what you're going to collide with in open water. But if you're in the polar regions, you, as we have seen, will have ice overhead. You may have ice keels, ridges of ice going down into the ocean ahead of you, and as well, you'll have the seabed. So it's far more difficult collision avoidance in the polar regions than in open water. And now you're getting these readings. How do you make sense of them? That's the real challenge, is in interpreting what your instruments are telling you. And your instruments are like fixed eyes. We've got the sonar beam here. You move the vehicle, the beam moves. Now, the object hasn't moved. There's still an object you've got to remember that's there, just you can't see it now because you've moved your sonar. So it's a real challenge of interpretation, and then you've got to determine what's the best action in this set of circumstances. And that can be difficult, and you can make mistakes in making the wrong actions. You may set the dive planes to climb. That's great if you've got open water up ahead, above you. You may want to go back along the track that you've came, the old-fashioned trick. If I'm lost, I'm just going to backtrack exactly along the track. Diving deeper under ice may be an option. And the last resort, you may have spotted in a photograph, a drop weight. I'm going to drop an excess weight, and I'm going to come up to the surface, come what may. That's the last resort. So how did these collision avoidance work out in practice? Well, back in the early days, here's 1997, when the team obtained a grant from the US Office of Naval Research, who were highly interested in what was going on here in Southampton. And they took the vehicle to Florida, they're Fort Lauderdale, the skyscrapers of Fort Lauderdale there in the background. And from a position about out here, a little map here, point A, the vehicle was launched. And so we've got point A there, shallow water. It was told to go out to sea at 10 meters off the seabed. So it's using its altimeter and its collision avoidance to stay within 10 meters of the seabed, but avoid the seabed. So if there's an obstacle, then it'll climb over it, like in there. And then after it had reached a waypoint, a location where it was told to come up to the surface, it does so at sea. It does so, and then that's when it gets a GPS fix. So that's when it actually knows where it is. And there's a jump there. So where it thought it was slightly different to where the GPS told it was when it surfaced. So this is an error of so-called dead reckoning navigation. And then it was told to come towards shore here and to head towards the beach at 12 meters off the seabed until the water depth was 16 meters, wherever that was. It wasn't programmed in latitude and longitude. Whenever it's 16 meters water depth, turn back and go back out to sea again. And that's when it turned back along there. So we were confident that the vehicle could avoid the bottom, it could terrain navigate at a certain height off the bottom, and it could turn round if the bottom got too shallow. So then a later scientific experiment now in 2000, we're in the Straits of Sicily. This was a well-traveled team. You've already seen them, Fort Lauderdale, Sicily, Antarctica. They went where the science was. So a group of scientists from the National Oceanography Centre wanted to make measurements in the trench here, or the deep channel connecting the eastern Mediterranean to the western Mediterranean. There's Sicily. This is a bank, Adventure Bank. Here we have North Africa. So you can see relatively narrow but deep channel connecting the eastern and the western Mediterranean. And so deep and so narrow that it's really hard for shipboard measurements to make detailed measurements close to the bottom here. So the seabed is in grey, and we're looking at the current speed. This isn't a science talk, so I just really want to show that they're making scientific measurements here of currents, and the currents change direction there from low, well, sorry, they change strength from low here in blue to a higher current right there on the steep part of the channel. And now we're coming back up, and that mission 239, splendid, scientists were overjoyed. Mission 240, so somewhat similar, go down, stay at the same depth, but then follow the cliff coming up, and there the data stopped, 380 meters. There's a photograph of the autosub. Now, I used to say the cliff cheated. Okay. So if the cliff is like that, that would have been perfectly fine as it was on mission 239. But the cliff, what did it have? It had an overhang. Okay. And so I go back to the difficulty of interpretation. The scientists or the engineers hadn't thought of, well, look, this cliff may have an overhang. What should the response of the vehicle be to an overhang? So when the vehicle was stranded there, and my lab director had to report to the Research Council chief executive, his question was, why didn't it engage reverse gear? So you can imagine the red faces when quite a simple response that could have been there in the control system wasn't called for. So again, when designing software, it's to be mindful of possibilities that may not be immediately obvious. But I did mention earlier that the vehicle was insured. So the insurance company, they arranged for an offshore services vehicle that had been working on some oil rigs in the Black Sea as she was passing through the Strait of Sicily. She deployed her remotely operated vehicle, went down on a cable, found the vehicle. It was pinging away, ping, ping, ping. We knew exactly where it was, it's just we couldn't get it back. And they took the photograph, and they took the arm of the remotely operated vehicle. They caught the stern plane there, and they pulled it out about 3 meters and let go. That was it. That was their job done. And it floated up to the surface. It had dropped its abort weight. It wasn't going to move. It was really jammed up against that overhang. So we got it back, but that's also a strength. So things can happen, but you can retrieve it, which is an important lesson. So now let's go, one of my top 2 expeditions that I was on, this one. So we're back Autosub 2, we're up in the Arctic, we're off northeast Greenland. There's the polar bears. Greenland is about 70 or 80 kilometers in the far distance, and between us and Greenland there is almost 100% sea ice cover. And what the scientists wanted to know was what were the characteristics of the sea ice from its edge here until about 70 kilometers toward Greenland. And they knew that we were over a shallow area, Belgica Bank. So the water depth here is 0 is where we started, and there's 60 kilometers, so 70 kilometers is over here or so. And this is the information that's come back from the vehicle after it was recovered. So there's a number of things here. The seabed depth was measured, so that's shaded in grey. And here's the first discovery. The existing bathymetry in the chart, that's what they thought they were going to be going. No, it doesn't look like that at all. Look, it goes down into a trench before Greenland starts over here. So the first discovery was a much better seabed bathymetry than was in the charts. And then in colour, again, we've got currents. So this time, a blue current is flowing to the south, and this is northward current, so a red current flows to the north. So different current structures over the bank and in the deeper water here. Quite a core of current. that they called the Northeast Greenland Countercurrent in red here over this trench. So they obtained that current information, and then on an expanded scale, showing outlined in this blue color, is the depth of the sea ice protruding down. So here, for example, we have a ridge of ice where two sheets of ice have come into each other, and there's so much force that they're driven down. And that's what we're seeing in that peak there, to well over 15 meters depth, and smaller ones there. And they were observed the thicker and rougher ice with these keels over the bank, and then over deeper water you can see that the ice is far smoother. So these were just some of the scientific outcomes from this, which absolutely delighted the scientists on board. The technical staff, when they got to their data, were absolutely horrified. Absolutely horrified. They plotted the actual track of the vehicle. I've simplified this. This is one-dimensional view going towards Greenland. As it came back, so here we have latitude and longitude. So Greenland is over here. The vehicle is coming back. It's doing its track quite nicely, thank you. Oops, it's got a loop. It's got a loop. So it's doing a collision avoidance reaction. It's coming back along its track. But that's no good, because Greenland's that way and home is this way. And then it turns. It effectively tosses a coin, because it doesn't know whether to go left or right. So it's tried up here. And it's tried, and no, there's an obstacle up there as well. No, let's try here. And then eventually it tries to the south and finds a way through, and then goes back on the track that's going to take it back to the ship. So they were horrified that that's what the vehicle encountered. And then, when I plotted that in 3 dimensions, we were even more horrified. It's climbing a ridge. It's doing this all autonomously. It's avoiding the bottom. There's a big ridge. No, it can't get across. There's an ice keel right over the top of the ridge. It's like trying to go through a post box. And it's going to try to the north now, back over the ridge. There we go. No, I can't. Oh, I've got to go back again. Right, let me try to the south now. Back over that ridge. Yeah, there we are. Right, and I'm going to dive deeper now. And then head up north, and then go back onto its track. So in 2004, that was the state of the art for the autonomous collision avoidance in 3-dimensional space of an autonomous underwater vehicle underneath Arctic ice. So with that success under their belt, back to the Antarctic underneath the Fimbul ice sheet, which is south of South Africa. And on mission 382, it came back with a sonar image. So this is image looking up of the underneath of the Fimbul ice sheet, which looks like this. It's 20 or 30 meters high up off the water, and like an iceberg, and 90% of it is underwater. So here we have almost 200 meters underwater, 200 meter thick ice. There is no escape back from here. So this absolutely wonderful sonar image of something that the scientists were astounded by. They thought the underside of these ice sheets in contact with water should look like that or that, not that. It completely changed their view of what the underside of an ice sheet could look like. So that was mission 382. Mission 383, I love this quote from The Guardian because it encompasses the sense of fun, the sense of achievement. This was mission 383, from which the vehicle did not come back. That's where it was, and that's where it still may be. Now, we did get a quote from the insurance company before we did this mission. And they said, well, we don't like to turn away business, but how about our premium is 90% of the value, and if you've still got it at the end of the year, we'll give you a bit of a rebate. And we said, well, thank you, but no thank you. And what the Research Council did, to their enormous credit, was to say, okay, well, that's a recognition of the risk. What we'll do is that we'll fund you to build another one. we'll fund you to build AutoSub 3 so that you have it as a ready-to-go replacement for science should you lose AutoSub 2. So we had AutoSub 3 ready to go because of the foresight of the Research Council. Never let anyone tell you that Research Councils are risk averse. Absolutely not. Absolutely not, when the science is this important. So we've lost AutoSub 2. What's the chance of getting AutoSub 3 back? And so, the director acknowledged the efforts of the team and the improvements in reliability since we lost AutoSub 2. But now the British Antarctic Survey want to use AutoSub 3, and they just don't want to go once or twice or 3 times underneath an ice sheet. They want to go 6 times. And they want to go underneath what some people call the Doomsday Glacier, Pine Island Glacier, in Pine Island Bay in the Amundsen Sea, which is one of the glaciers buttressing the entire West Antarctic ice sheet. And Pine Island Glacier is melting at the fastest rate, together with its neighbour Thwaites. There are serious issues in Pine Island Bay. That's why they wanted to go there. But they wanted 6 missions. And I came up with an answer. The missions, give them test numbers, how far they wanted to go. They wanted to go 60 kilometers in, 60 kilometers back 3 times. And then the probability of survival. And I said, the probability of survival is 76%, I said. How on earth did we get that? You have to give. And I should say that the director at the time, his first degree was an applied mathematician. I could not pull the wool over his eyes. Okay. So how do we achieve reliability in a one-off artifact? This isn't a manufacture of thousands of items where you can take a sample and test them to destruction. Rapid test them, accelerated life tests, and come up with the figures. It's a one-off. So in part, it's reliability by design and proof testing. So to go back to the motor, I find it hard to read engineering drawings. But what this motor is, it's an inside-out motor. So the windings on a normal motor that you might find in a piece of apparatus, a drill or something like that, the windings rotate. Here, the windings are fixed, and permanent magnets rotate on the outside of the windings housing. So they're rotating in seawater. The coils are inside an oil-filled housing here, and the magnets are on large diameter bearings. So this is a Lossier motor, but they are Xylan coated, which is a very low friction material, and Inconel to avoid corrosion bearings. So you design out the need for a shaft seal to operate at high pressure. You design out and you test it in the pressure test there using a permanent magnetometer. So now we have underway faults. The team have, just like a pilot would, a checklist before missions, their pre-departure checklist, which catches a lot of things before the vehicle goes in the water, before it is launched, or while it's still alongside the ship. But still you come up with a histogram of the number of types of different faults. And human error was the major one. And the team were very good at saying, I got that wrong. I set a wrong variable. I made an error. Let's log it. Let's learn from it. They were very good. Then software fault, 4 of them. Software faults after last week are perhaps of quite some interest. But here's a lurking software fault. It was in the North Sea on a herring survey, and the start was fine. So this is the east longitude, and then latitude north here, and this was its track. And over 10 hours, it was supposed to run 54 kilometers to the northwest. Everything was absolutely hunky-dory until the 10th hour, when it didn't go forward anymore. It was going around in this racetrack pattern after 10 hours. And it was a simple software algorithm fault, converting from latitude and longitude to east and north, which it needed in meters. One way it was using that formula, and going back the other way it was using that formula. It they dropped the plus lat bit in going back. Now that meant that there was no error at all on an east-west course. Your latitude was constant. You'd never see this bug. If your course was north-south, you'd never see this bug. It had been there for over 30 missions. Only when you went at an angle and only when you went long enough that the error built up would that kick in to make it go round in a racetrack. So, software faults can be very difficult to find. So there is the probability of a fault happening, but there is also the impact of the fault when it does happen, and that depends on the environment. Now, over the last 40 minutes plus, you've actually been attending a training course to become an expert in judging the risk of losing an autonomous vehicle. So you've heard this evening that AutoSub is buoyant. It's going to rise to the surface. So if the motor stops, the vehicle will rise. If something is wrong, it drops a weight and comes up to the surface. It has a GPS receiver. It knows where it is. It has a SATCOM phone, so it can call home once it's on the surface. And a research ship will be in the region. So you're the experts tonight, and the fault is that the propeller has stopped turning. Okay, that's the fault that's happened. It's 50 kilometers into a mission. We've got the ship nearby. Now, is our chance of getting AutoSub back better or worse than 50-50? Now, let's think of case one, open water. It's not a dead calm. It's a bit rough out there. So, is the chance of getting it back better than 50-50? Who thinks better than 50-50? Okay, yeah, good showing, but not 100%. And who thinks it's worse than 50-50? Okay, yeah, no, and a good number. That's terrific. Absolutely right. And when you ask, no offense, real experts, this, you do get that. You get pessimists and you get optimists. And what you mustn't do is to average them out. You must talk to the pessimists and find out, well, why did you think that? Because they may have something that will bring to the case. Now, that was open water, exactly the same conditions, but now I've got sea ice. It's 2 meters thick, and it covers 90% of the sea surface. So now, who thinks we've got better than 50-50 of getting it back? No, going once, going twice, no. Lower than 50-50. Yeah, I agree with you, absolutely. So it depends on the environment. So we can borrow from actuarial science and medical statistics for a graph known as a Kaplan-Meier expected survival. And normally you'd have age from here, 0, infant, to, well, not 300, but, whatever may be, 90, 100. And this graph would drop. That would be mortality. But now I've got the probability of survival against range. So we've borrowed their form of graph. And for all of these incidents, like we've gone through, when we put all those together and look at underneath ice shelf, I'm going to just do this one in black, there's sort of an infant mortality. There are faults that happen that can make the vehicle potentially be lost, and they occur within a shortish distance of the start. So what became the procedure was that, yes, before you go under ice, do not go under ice here at 0, but let's have it going round and round the ship out here for maybe 30 kilometers in circles, and let's bottom out that part of the curve, and then our reliability will be, our probability of encountering a problem will be much less. We'd have caught those early type of issues before we committed to going underneath the ice. And that's what was done. And so the vehicle went to Pine Island Glacier. It carried out 6 missions underneath the glacier. So the black is the open water of Pine Island Bay. This is the edge of the ice sheet here. There's Pine Island Glacier. There's the edge. And this is in a 100-kilometer scale there. So mission 431 was the one that penetrated deepest towards the grounding line, somewhere here where the ice met the seabed. It exceeded expectations, 932 kilometers under the glacier in all. And the vehicle came back. But Here's an annotation that I did that's rather difficult and rather simple, and I wish that I knew somebody from George Lucas Imagineering how to visualize this better. But we're going to do a three-dimensional track like we saw earlier. So we've got latitude up here. The vehicle is going to head south underneath the glacier. We've got longitude going along the bottom here. And then we've got depth from 650 meters down to 950 meters below sea level. And here we've got between 400 and 600 meters thick ice above us. And then there are going to be little dots that appear here. ADCP up is our upward-looking sonar. So when we see a dot here, the ice is above us. When the forward range here is going to be the range of the sonar looking in front of us here, we'll see dots. And their zero is here, is against this line. So if they come to zero, they'll bang along the bottom here. And this is the collision imminent. This is the klaxon going off. Do something. Collision imminent. And along the track of the vehicle, we've got the heading, which will show as a green line, the direction of the heading of the vehicle, and red is commanded, what it's being told to follow that direction. Now, they should be the same. When the vehicle turns, then they'll deviate slightly from each other. And I'm going to run this now, so from the vehicle going in towards the grounding line, everything is fine, it's following the bottom. It's going to turn round, and then it's going to come and follow the underside of the ice now. There it is. It's coming up, it's following the underside of the ice. It's gone right up. We've got these things. We've got a collision imminent, we've got zero forward range, and we've got a big difference between heading and commanded. The vehicle isn't going where it's being told. And we've got all of these ups, forward range, collision imminent, and now it's dived down, it's turned round, and it's coming back. So this collision avoidance, it didn't do well avoiding collisions. And it gave up, and it dived deeper away from the ice. What had happened was that it was going along, tracking the underside of the ice, and then you may have seen pictures of crevasses in ice on mountains and glaciers, a big cavern or chasm in the ice. There was one on the underside of this ice sheet, a chasm underneath. The ice suddenly disappeared. So the vehicle said, okay, I've got to follow it. I've been told to follow it. I'm going to rise up into the chasm. It didn't know it was a chasm. And then, of course, it was faced with the end of the chasm up ahead of it. And then it tried to turn. The chasm was still there. It tried to turn. It kept bumping against the edge of the chasm. And that's when it decided that it had to dive deep before turning around and came back. So again, the level of autonomous collision avoidance was absolutely brilliant. And I'm not a boastful person, but this is science that was in nobody's footsteps. This was the UK doing something unique back in 2009. And no one since has been back underneath Pine Island Glacier with anything like that achievement that you've seen this evening. So to conclude, why is this important? Again, a wordy slide. But it's there in the scientists' own words, that those evidence gathered by AutoSub operating beneath Pine Island Glacier, that it was recently grounded on a ridge, which we saw there, and that warm water now flows underneath into that cavern space. And it's moved downstream of the ridge. And just to read their last sentence, the pace and ultimate extent of such potentially unstable retreat are central to the debate over the possibility of widespread ice sheet collapse triggered by climate change. There is nothing to stop Pine Island Glacier retreating another 300 kilometers now. It's going to go into deeper and deeper water as it retreats. That is inevitable. So that's informing a debate by the artifact AutoSub, the precursor to Boaty, designed and proudly built at Southampton. Thank you.